We are now in a position to finish this course with some of the most advanced techniques that we have today to look at small objects. These methods rely again on incoherent imaging. They rely on fluorescence microscopy. There are variants thereof, and using tricks allow users to gain resolution in images that's better than lambda over 2Na. And the first technique is easy to understand, and that's the technique that we will talk about today, and it is called single molecule localization microscopy. So two of the 3 Nobel Prize winners that I've mentioned, Eric Betzig and Bill Murner, are credited with inventing these methods and got the Nobel Prize in 2014 for this discovery. The last technique is called STED, Stimulated Emission Depletion Microscopy. It is a confocal imaging method, and that works slightly differently. And for that technique, Stefan Hell in Germany got a third of the prize. And so what I do now is I will switch over to the lecture notes on my screen, and I will begin by talking about this first method that's called single molecule localization microscopy. And so you can think of this technique as optical pointillism. You know, you control the fluorophore on and off rates. So paradoxically, this method requires you to switch the molecules into an off state much more than into an on state. You want to actually get the number of photons emitted to be very low. So at any one time, you try to reduce the number of molecules that emit at the same time, and you will see why we require this and what this allows us to do. I will go straight into the method. You can go and read through the key concepts after you've seen the lecture. So when you revise this gives you pointers about what to look for and what concepts we are dealing with. So here's the concept of single molecule localization microscopy, which comes under many different names, but all mean the same things. All work by this principle. Physically, they're identical. And so here you have an image, a cartoon. This cartoon is just there to illustrate the principle. So it's a computer-generated image of a small object. So you see, let me just turn on the laser pointer. You see down here the scale bar. This is about 2 micrometers. And so this object has lots of fluorophores, and the fluorophores are emitting light. Each fluorophore emits a blob of light. That's the point spread function. And the sum of all these point spread function gives you this blurred image because the molecules are too close to one another, so you cannot distinguish them. And so what I now want to do is, let me just suppose I'm able to switch most of these molecules off. Let's switch them off. That, for example, we only have 2 molecules remaining in the on state. So these 2 ones here. So what do you see here on the camera? So you see these pixelated images on the camera of the point spread function, corresponding to a molecule that looks here and a molecule that looks there. So what you do in single molecule localization microscopy is, if I have an individual point spread function, then what I do is I fit the centroid of that point spread function. The point spread function is a Bessel function We typically approximate this for computational purposes with a Gaussian function, because a Gaussian and a Bessel function are very similar. And for the purpose of this technique, a Gaussian is much more computationally efficient to work with, and it makes no difference to the accuracy or precision of the method. So I have this Gaussian distribution, say, of photons distributed over the pixels on my camera, and then I just say, okay, the center of this distribution is where my molecule is located. So I make a dot. So here's molecule 1, there's molecule 2, and then I keep going. I do this again. I do this, I keep switching on lots of different molecules. I can never say precisely which molecules will switch on next in the next camera frame, but I take lots and lots and lots of exposures on my camera and keep recording the positions of the molecules. And in fact, what I now get is the location information from the molecules on the sample. And that location information is resolved much more highly than the point spread function width itself, because I'm not actually interested in the width of the point spread function. I'm just interested in knowing what the centroid is. So if I have a Gaussian distribution, if I have enough photons in that distribution, I can get the centroid located very accurately. And so that's the principle, and you can see why we need to switch off most of the molecules. Essentially what I'm doing is I'm making sure that by having a sparse subset of fluorophores only on in each image frame, I see the point spread functions separated, they don't overlap, and I can fit the positions of the molecules with good accuracy. And in fact, the fitting precision, the localization precision of the molecules is now just given by sigma over the square root of n, where n is the number of photons that each molecule emits. An organic molecule can give tens of thousands of photons before it bleaches, so we can excite it many, many times, and we will collect the, in a very short time. And so each one of these PSFs that we have will contain lots of photons, signal photons. And the PSF now, the localization precision, is the width of the diffraction limited PSF. Let's say 300 nanometers divided by the square root of n, where n is the number of photons. So let's suppose I have 10,000 photons, then in theoretically, the localization precision for the molecule goes from 300 divided by the square root of 10,000, which is 100. 300 divided by 100 is 3. It goes down to 3 nanometers. 3 nanometers is difficult to achieve, but you can routinely achieve 10 nanometer resolution with a few hundred or a few thousand photons per molecule. So that's the principle. That's all it is in this technique. So the art really just is to prepare the sample in such a way and to excite it in such a way that we can only switch on individual molecules, a subset at any one time for each image frame that we take. Here you see a real recording from downstairs in the laboratory. These are single molecules, single dye molecules of Alexa 647 dye. It's one of the most commonly used dyes for single molecule localization microscopy. They are in a buffer solution on a cover slip, and these flashes of light are these individual molecules we're talking to. And you can see only in fluorescence can you do that. You see the bright signal on the dark background. This wouldn't be possible with any other method, right? So we can routinely detect these individual molecules. They blink on and off, and this information does nothing. But actually, when you then look at and assemble the location position, you get the images back. You get information about the images back. I should say about the sample back. I should say that is better resolved than lambda over 2NA. I should say that you need to be careful in interpreting these images, in the sense that you always need to be aware that what you are looking at in the super resolved image, in the single molecule localization microscopy image, is not the sample information directly. It is the localization data, and you need to be careful sometimes to interpret this because there may be artifacts that come from that fact. that lead to misinterpretation. But I'll show you some examples where this technique works very well and the kind of things that you can do with this. So here is the workflow. What you need to do is you need to find a fluorophore that you can switch off. That's the key. You need to be able to switch most of the molecules off. In fact, if you have densely labeled samples, you must make sure that within one point spread function on your camera, you have definitely not more than one molecule on. In fact, you want it less sparse than that, but that's the minimum, right? So you need to have less than one molecule on in your field of view per PSF area, right? Because otherwise we can't distinguish the PSF. So in practice, you make it even less sparse than that, right? Sorry, even more sparse. Even more sparse meaning even fewer molecules need to be on. So you find a suitable fluorophore that you can switch into the off state and only a few on. You label some living cells with this in the usual way, just the same way as we've already discussed in one of the lectures. You capture thousands of images. Here you see the big disadvantage with this method. To get one super resolution image, you need to capture thousands of images and capture the localization data. And you can imagine, first of all, you get huge data sets, and then you need to computational process the location positions, so it takes time. So this takes minutes, typically, and is not good for live cell imaging for that point, because the cells will move and things inside will move, and then the localization data is useless. So it only works on fixed cells, which is a disadvantage. Then you localize, and then you reconstruct. So there's a step that involves the sample preparation, the actual measurement, and then there's an image processing task in there too. So the question is, how do I switch molecules off? So how do I do that? And to show you how that works, at least in principle, I revert back to my paper viewer, the previewer. And so here is switching fluorophores on and off. So in the normal fluorophore, we have our usual lower state and the upper state, and so let's call that state 1 and state 2. And so what happens in a normal way, we've seen this when we went through the fluorescence rates. So we drive population up, and so I'm just doing this now pictorially. And so now before I do this, let me put something else in here. I put in some other states. So in normal fluorophores, these electronic states turn out to be singlet states. You may remember this. You remember this from your chemistry, what singlet states are. So this is where the spins are parallel in the sample, right? So these are singlet states, and then there's also something called a triplet state, so where they're not aligned, and so the spins, and so you remember that these have different chemical properties and so on. But what happens, so we never discussed this in the past, and because it wasn't really important for our purposes. Usually when we excite fluorescence, I'm just drawing this now pictorially, a photon excites the system. It comes back down either by quenching or by fluorescence. I can pump it back up again in the molecule and so on, pump it back down and so on. And I can do this cycle many hundreds of times. But actually, there is a certain possibility that the molecule will land from this excited state, not in a singlet state, but in its triplet state. So the spins flip. And you don't need to remember the details of this, but fluorescence happens between singlet transitions, so the singlet ground state and the singlet excited state. And so there is a certain probability that after a few cycles that the system just will flip, and you will, this can be assisted by collisions or by the presence of paramagnetic species. The details are not important in the solution. And so once it's in that state, it's actually very hard for the for the molecule to return back down to the ground state, to the singlet ground state again, so that it can participate in fluorescence again. Because in quantum mechanics it turns out that a transition between a triplet state to a singlet state is what is called electric dipole forbidden. The details are not important, but actually, so this transition is very, very, very unlikely. And so as a result of that, so the lifetime of this is very, very large. In fact, this process here, the slow return, leads to a process that you all know, which is called phosphorescence. So phosphorescence is a transition from a triplet to a single transition. Because it's so unlikely, the photons come back very slowly. And so something that you excite into this triplet state will glow forever after you've excited it. And of course, the old watch dials exploited this process. So and normally in fluorescence, we don't have to deal with this, right? But if you just cycle this a long enough time, most of the molecules will end up in this triplet state, and then the system becomes dark. So compared to the normal lifetime that we've discussed so far, so the fluorescence lifetime, I'll put this in like that. We have this happens at the rate A21 as usual, and this happens at the rate K phosphorescence. So we have maybe A21 is 1,000 times faster than the rate of phosphorescence. So what that means is it's much more quickly and much more likely to happen that the system comes down this way than that way. And that means, in other words, that the phosphorescence lifetime is maybe of the order of 1,000 times longer than the fluorescence lifetime, the normal standard signal lifetime that we've got. So in fact, all we could do is we could just flood the sample with light for a long time until most of the stuff happens over there, and then we automatically switched about 999 molecules off because they're dark in this T state, and it trickled back only very slowly. But so we have an on-off ratio now of about 1,000, of about 1 to 1,000. So it's off 1,000 times more longer than it is on by doing this trick. That's nowhere near enough to get enough fluorophores off. You would still have massive overlap, and you would not be able to isolate the single molecule point spread functions. So you need much better control of the off rate. And in fact, there are dyes that you can turn off by adding a chemical compound, usually containing thiol compounds, a buffer solution, and that reacts with this triplet state. So there's another state that you can access by adding a thiol buffer, and the system reacts in this excited triplet state, and it goes into what really is called an off state. In this state, the fluorophore really does not come back down. So now, from this off state, let's call this T off, or to return from this state here, we now have an enormously long-lived state here. And simply you achieve it by first doing this trick, putting the correct buffer inside the system that you're looking at. The buffer then reacts with this excited triplet state, and then the molecules will really stay in this off state for a very long time, because this T off is so much longer. So just to give you these are just ballpark figures, whether they can vary quite dramatically between individual systems, but just to give you an idea, so maybe the fluorescence lifetime is 10 nanoseconds, so that's 10 to the minus 8. Maybe the phosphorescence lifetime is 1,000 times bigger than that, so let's make it 1 microsecond, let's say. And then, but the lifetime, this off lifetime is of the order of 1 second. So you can see that, so we have a difference now of 10 to the 8 of the rates of this rate compared to this rate. So that really will mean that most of the molecules are dark. And so, in fact, what this thiol buffer does, it reduces the state. So this is a reduction. And you can now control how many trickle back so they become active again by putting an oxidizer in there. For example, you know, this could be dissolved OH or something like that in there. So the point is, by doing this trick, we have reduced the on to off ratio by a factor of 10 to the 8. Okay, and that is essential for this technique to work. This technique is called storm, or also de-storm in the literature. It is called, so storm stands for stochastic optical reconstruction microscopy. And the direct is something that people have put in. There have been lots of debates who's invented what first and so on, and so everybody gives different techniques their own acronyms because they want to be famous and so on. But in fact, all of those are the same principle of single molecule localization microscopy. The term stochastic means that we can't really know at any one time which fluorophores come on and off. We don't know whether this fluorophore will switch on. It doesn't matter. All you need is that in your image you have a sparse enough set of fluorophores on so that the point spread functions are separated. And once you achieve that, you just localize positions. You keep doing this until most of the fluorophores have been on at least once, right? And in practice, that requires you to take 10,000 images or so per image that you want to super resolve. And the direct here means that, you know, in the past you can think of several ways of achieving this switching, but this switching chemically with these buffers is a very convenient a way to achieve this, and because you don't need to engineer very funny light switches on a molecular level. That people have done this by turning molecules on with light and other things. Here you just turn them off by putting this quenching buffer in there, and so that's why people say it's a direct method. So you just achieve it immediately. So here, going back now to my computer, you see how this works. So you initially put light onto the sample, and the sample will. Am I on the computer? Yes, that's right. So you can see this here. So initially the sample will give you a flash of light. It will trickle down to the triplet state, will then chemically react and go into the quench state. So initially you get a flash of light, then it all goes dark, and then you are in this sparse state, and then you have this very slow trickle back from this off state, and you can control it by essentially changing the redox reaction with your buffer. So how exactly physically this works, people don't fully understand yet, but here is a dye, a cyanine dye, which is similar to this Alexa 647 that I showed earlier. So it is again a highly conjugated dye containing rings and also these linear conjugated bonds here. And so once it goes into the triplet state, it can be attacked by a thiol reaction. And so actually what that is thought to do is that it actually it interrupts the electron transfer, the delocalization across these bonds here. So by having this thiol attack, you create a charge disruption, and so the molecule turns into an off state. It doesn't fluoresce anymore. And then, of course, by oxidizing again, you can get rid of it and you can switch it on, so you can actually control a little bit about how much you're putting back. So if the rate is actually too low and none of the molecules are on, you just may add a bit of oxidizer, change the reducing buffer a little bit, so that you can control the stochastic rate at which the molecule can come off and on. And that's the idea behind it. So what's the resolution that you can get? Well, the standard way of thinking about this, I'll go back now quickly to the overheads, to the visualizer. The resolution considerations. How much better is the location information resolved if I'm is the location information resolved compared to the fluorescence? So let's just have a look. Resolution consideration. So the first is according to the Rayleigh criterion. We had mentioned this, perhaps not so explicitly, but we had mentioned that we say that two fluorophores are resolved. Let's say this green one here and this red one here. We say they are resolved if if the minimum of the PSF of the green fluorophore shown here, I mean, they're not green and red in principle, it's just so you can see the difference here. When the minimum of one falls on the maximum of the other. And that is the Rayleigh criterion, because then we can clearly PSF red, and this is PSF green fluorophore, or call it 1 and 2 if you so want, right? And so we know that that distance here, delta x, that needs to be delta x is equal to 1.22 lambda over 2 Na, right? So we worked this out actually when we in an earlier lecture. It's roughly lambda over 2 Na, right? But it's if you do it exactly for a Bessel function, then this turns out there's a factor 1.22 there, which we actually did in one of the early lecture. Turns out that this is quite a so this would be what would it be? Maybe 200 nanometers or something like this. Depends on lambda, of course. Depends on Na, but maybe that's what you can achieve. It turns out that this Rayleigh criterion is a little conservative, and you can resolve things that are even closer together, and the criterion that is often used to say I can resolve something is called the Sparrow criterion. And the Sparrow criterion in practice means that so this would be for standard optics, for standard fluorophores. It means that that if you have these two things together, and here's red again, so I've done this badly. God, let's do it again. And then I put this one. You say that the overall envelope now is the sum of these, right? And the Sparrow criterion says you resolve when there is a dip in the overall envelope, right? So they will of course not be resolved anymore if you can't see that dip here anymore. And so you just have to differentiate the point spread functions themselves to see whether they're close enough so that the dips becomes invisible. And just to be clear, so this is for standard imaging, right? So with the standard PSFs. What we do in localization microscopy, when we actually fit PSFs, we do fit the PSFs approximating, in practice, approximate the PSF with a Gaussian function. You would not use Bessel functions because computationally that's really expensive, and it's much quicker to fit Gaussians to the point spread function. So one typically uses in this is a 1D distribution, but the equivalent is true for the 2D case, but along x the profile would be something like e to the minus x squared over 2 sigma squared, where sigma is the PSF width, right? And so the point is now that what we need is if we want to resolve two molecules optically, we need to we need to make sure that the sum function, so this one position is here, the other position, so that's x1, and this one sits at x2, and x1 is here. We need to make sure that so that the Gaussian x1 squared here plus x2 squared on the other side, that the envelope of those two has a dip in the middle. So otherwise you cannot see that, and that is you will do an exercise on that to see whether in practice you could resolve this. Now, of course, in the single molecule case now, what you want to do, what you do is you just switch one of those off, and all you're interested in is the center. You switch the other one off, so you only look at that one. You locate the center, and how accurately you can locate the center just depends on the number of photons, as we've discussed. Okay, so these are resolution criteria. This is classical optics, best you can do. You can then compare how much would I see with this single molecule localization microscopy technique. How much would I improve on the Sparrow criterion? There is, for single molecule localization microscopy, another very important consideration, and that is the Nyquist theorem. So labeling density and Nyquist. And to show you what I mean by that, if you have small objects, obviously you need to have enough fluorophores present to give you enough information about the underlying structure. And just to show this quickly, I go back to my computer screen, and you see here the word Nyquist drawn out with molecules positioned at particular positions in a matrix. And then, of course, if you do not have enough molecules, the information goes. And so clearly what you need is to label at twice the frequency of the highest spatial frequency that you have present inside the sample to be able to see the structure. Right, so that's the sampling theorem or the Nyquist theorem. So that actually is a problem, so because actually you need enormously high densities of fluorophores, and that actually to get super high resolution. If you want resolution down to 10 nanometers, you need a fluorophore at every 5 nanometers, right? So that is actually getting towards molecular level distances, and that may in some ways not be feasible or not practical to do. But you can get for some samples, this is topology dependent. If you have very simple sample topologies, lines or dots, then actually you don't have to resolve the full topology, because a line, if you know it's a line, you just need a few dots along, locate those very well to be able to see the line. Here you see one example where this works very well. This comes again from our own research. So what you see here is an image with a high numerical aperture lens, a fluorescence image of a protein called A-beta, and this protein A-beta forms fibrils in the brains of patients who suffer from Alzheimer's disease. And these fibrils then clump and they displace and kill brain cells, and this is of course what leads to dementia. And the microscopy image on a cover slip of these labeled samples looks like this. And of course here you see a scale bar, 500 nanometers, and you see these fuzzy images because each fluorophore on these fibrils gives rise to this blob of light. It's a convolution of the PSF with the sample structure. Now, the trick from Myrna and Hell and using this, Myrna and Betzig using the single molecule localization microscopy idea turns images like this into images like that. So we now get really finely resolved structures because we have switched molecule by molecule, located the position of the molecule, and drawn a dot, and then what we see is the outline of the fibril from the localization data. So this is the same image, and if you now look, if I turn this on, you see this image turning into the super resolved data. So it's really a dramatic improvement. So we really see now life at the molecular scale directly. The only problem is to generate this image takes 5 minutes of data acquisition. And it takes so long to switch. So this is the general principle that I mentioned right at the beginning. You trade time for resolution. Space against time. It's Fourier transform pair. It's all nicely related. If I want more information about the spatial dimension, I have to give up temporal information. Remember Golgi, Camillo Golgi. Remember how he found the neurons with the black reactions. It's exactly the same idea, right? So only those neurons turned black where this reaction took place, but the reaction is so terribly inefficient that only a small subset of neurons was visible in each image. So you get a few, in any one snapshot, you get very high level information about something, about a small subset of the sample. All super resolution methods work in that way. You trade speed for resolution. So here's another one. This is actually a cell. This is again from our own research. It's a fixed cell. So this one has taken up this is a neuronal cell. It has taken up the amyloid fibrils. They aggregate inside, but you have no idea from a standard fluorescence image what these structures look like inside the cell. But by doing this with optical super resolution, you suddenly turn images that look fuzzy and hazy like this on a good microscope into these super resolved images, and you suddenly see, actually the fibrils inside the cell inside are all broken up, right? So the cell's obviously dealing with it. The process of this protein clumping is very different inside the cell compared to what happens in the test tube. So here are other examples. So here I'm turning the same, just to come back. So if you look at the lower half of the image on the left, this is actually what the super resolution image turns that into. So you get massive increases in contrast. You see some of the fibrils now clearly, and you get molecular scale information. Here are again images from work that we did on imaging viruses. That's obviously something that's now of interest to many of us. These were images from virus particles. These virus particles here is HSV1. This is the herpes simplex virus. Not quite as dangerous as the one that we're all concerned about at the moment, but nevertheless can be a nuisance. And so this virus particle has a size of about 150 nanometers or so you can't see it on the normal microscope. But using super resolution, you turn this image into this. And this is really what you see. You see actually the envelope structure of the proteins, and you now have this advantage compared to electron microscopy that I can label specifically individual proteins. So this is just one protein we're looking at, and I can map out the position of different proteins inside this virus structure by just labeling each protein with a different antibody. And by doing this and using computational fitting, I can get the most likely relative position of these protein shells and get the architecture of the virus. So you can see you get phenomenal resolution using this. So here is the radius at which these molecules appear, 121.8, 150.6. These are nanometers, 10 to the minus 9 meters. So you can then get pictures from data like that that enable you to get the likely structure of the virus and how it's assembled. So this protein here is on average closer to the center of the virus particle, and perhaps this one out here, and that's reflected in their relative positions. And you can get this from optical data. 10 years ago, nobody would have thought that this is possible, that you get this kind of resolution and molecularly specific information from systems like this. And then I should say that I said that you can't do this in living cells. If in the way that we talked before, but in fact there are sometimes situations where the density of the molecules that you want to see is so low that the likelihood of point spread function overlap is very small anyway. So you do not actually have to switch the molecules off because there are only so few molecules there in the first place. And this is then the field of single molecule tracking, and that means you can use the same principle of fitting point spread functions in living cells, right? The only proviso is that you have a low enough density of fluorophores present. So here's another example. So in fact, what we've done here is we've developed a method that allows us to track how a protein is being synthesized inside the cell, and we get flashes of light, and the flashes of light tell us the protein has been translated inside this neuron. It's an axon here. In fact, this translation is taking place in the distal parts of the cell, and so we get a flash of light, and we know a particular protein has been made. In this case, it's a cytoskeletal protein. It's called actin. So we make a fusion construct. The fusion construct is turned into protein by the ribosomes in the translation part of the machinery, and then we get a flash of light when the polymer comes off the ribosomes and folds into the correct configuration. And it becomes a fluorophore, of course, because the GFP is attached to it. We get a flash of light. We can localize that flash of light and use this fitting technique to actually precisely target where that event has taken place. And we can then correlate this to functional information, and in living cells. So we can see, for example, that the protein we're looking at here, more of it is produced inside cells when certain chemicals emitted in the brain are present, so-called neuronal guidance cues. So we can mimic this by taking the neurons, putting them into a glass slide, and then putting these chemicals onto the outside of the cell. And what you see are little flashes of light. I'll play this again. Let me see. So we have this outline here, then of the neuron, and then when we look at this fusion construct, so you see flashes of light appearing down there about now. Now you see these flashes appearing. Each one of those flashes is one new protein synthesized inside the cell. And this correlates directly with administering these cues. And what this tells us, so you see these are events, these are essentially protein synthesis events inside this thing. And this can be correlated directly with diseases that cause growth defects. It can be correlated with drugs you may administer to play with certain processes inside the neuron, and so on. So these are powerful research tools that are enabled through this trick of single molecule localization microscopy. So if you want more details, you can read about these in papers that are shown here. But for the purpose of this course, it's just giving you examples. So you can do single molecule localization, but you need low densities of fluorophores. And in some cases, this condition is given also in live cells, in which case this technique is called single particle tracking, because the particles will move, but it applies nevertheless, and you get super resolution about these events. I will skip the rest of this lecture because it's not really important. You can read more if you want. The references are there, but they are just there as examples in case you want to pursue some of this in further detail. Okay, and with that, I finished this lecture, and I'll see you for the next lecture, which is on stimulated emission depletion microscopy. Thank you very much.